Well, good afternoon after the break. I know it's a little bit hard to come back to the room here from the getting away from the nice scenery, but I hope you will fill up as I continue my talk. As Alfred already mentioned, it's a more on an applied side, less physics, and also more about real analysis of diffusion weighted imaging. We already know from this morning that diffusion weighted imaging can be applied basically for examining two types of questions. One is it gives us inferences about the brain microstructure, the cell size, integrity, composition, and so forth. And another thing is that it gives us the opportunity to examine the structural connectivity of the brain by fiber tracking. But in a real study, you're usually faced with one of two research questions, and I broadly state that is there a difference in brain microstructure, or is there a difference in the structural connectivity between two or more groups, or between two or more measurements, or two or more brain areas? So those are the fundamental research questions that you're likely to address, unless you want to do a single case examination, which is very rare. When you're trying to address this question, then you face several challenges, and I broadly state them here. And regardless of what type of analysis you do, you have to solve these challenges, you have to solve these questions. You need to make decisions on the acquisition. I'm not going into detail here because we have talked about that in more detail this morning. You need to do some pre-processing of the data. You need to correct for eddy currents, for head motion. You need to decide on data cleaning, smoothing, outlier detection, and so forth. You need to decide on the appropriate diffusion model or on the appropriate fiber tracking algorithm. We had some ideas this morning. Diffusion tensor model is a most commonly used model, but there are many others out there. But even if you chose on a model, you need to decide which parameter to analyze and how to interpret that. And then when you do a group comparison, you have one major challenge, that is the normalization problem. And we had some question during the discussion section this morning about how to best normalize individual brains in order to perform a group comparison. And my talk is primarily on this normalization issue because we have discussed the other aspects before. And finally, you need to do some inferential statistics if possible, and I recommend you to consider that because we want to make some inferences about true differences and not just having some description of our data. I'm not going into detail for the diffusion models that we can analyze because it was discussed in more detail this morning, but just as a rehearsal for those of you who just came here, the most common one is the tensor model. And the tensor model can be described by an ellipsoid composed of 3 eigenvectors and 3 eigenvalues. Based on this tensor model, you can derive certain parameters. The most commonly used one are mean diffusion, radial diffusion, axial diffusion, which are measures of diffusion strengths. And you can also quantify the fractional anisotropy, which can be thought of the normalized variance of the eigenvalues. What I'm going to focus here is what type of normalization procedures you can use for a group comparison. And you can broadly classify the types into 5 categories, which I tried to elaborate here a little bit, and then focus primarily on the last one. I did not list here one that was this morning raised briefly by Alexander Liemans, that is the histogram approach, because it's a little bit coarse. It can be useful for some questions, but it's probably not the major choice. especially in the early days, but still possible and good strategy could be a region of interest approach. You define regions of interest based either on the macrostructure, you identify certain target regions, and then you examine the diffusion properties within these target regions. You can do that based on the structural MRI, or you can do that based on diffusion imaging, based on fiber tracks, which is known as quantitative fiber tracking. Or you can choose a more general approach, a whole brain analysis approach, and here you have basically the choice among three options. You can pursue a voxel-based analysis or voxel-based morphometry approach. You can do the so-called tract-based spatial statistics called TBSS. Alexander Lehmann this morning has briefly mentioned that. And one approach that I hope I can convince you is a very meaningful approach for diffusion analysis, that is a service-based analysis. If you pursue a region of interest approach, the basic steps of your analysis are that you pre-process your diffusion data, you calculate parameters based on your diffusion model, and then you identify regions of interest, usually based on a T1 weighted or a T2 weighted image, and ideally by some automatic segmentation algorithm. Sometimes it was done manually, but manually segmentation is not the first choice. And then you extract the mean diffusion measure within each of these ROIs and brains, and you compare it across subjects and ROIs. This approach has several benefits. It corresponds, you have a good correspondence between the brain microstructure and the brain macrostructure, and it's a relatively straightforward analysis. So even though it's a relatively old approach, for some study questions it may still be a good choice. Nevertheless, there are certain limitations. It's not a whole brain analysis. It requires a priori hypothesis about the relevant region of interest. It further assumes that there is a homogeneity within the ROI, and you should have some automatic segmentation of this region of interest. Here an example how it has been applied in the past by Pfefferbaum. They looked at fractional anisotropy and intervoxel coherence due to aging, how this is changing due to aging, and they identified certain regions of interest, several subdivisions of the corpus callosum, and they found that fractional anisotropy is decreasing in the anterior portion of the corpus callosum, but also intervoxel coherence is increasing in that part of the corpus callosum. Then I mentioned that you can identify these regions of interest based on fiber tracking, which is known as quantitative tracking or fiber quantification. The basic steps are the same, except that the ROIs are not defined on anatomical space, anatomical images, but instead based on fiber tracking. This again provides a good solution of the correspondence problem. It usually works semi-automatic, and it quantifies the microstructure along these tracks. The limitations, however, is it's again not a whole brain analysis. It's limited to established tracks with known trajectories and anatomical landmarks. So if you don't have an a priori hypothesis on the track that you're interested in and on how to do the fiber tracking on these tracks, it's getting difficult. And maybe another downside is it requires relatively lot of processing. Here are two examples from different software tools that apply this approach. One is an add-on of the FreeServer software pool called Dracula, Tract Constrained by Underlying Anatomy. And this tool allows you to automatically segment 18 tracks within the white matter and to quantify diffusion parameters along these tracks. On the right, a second example that is based on the AFQ tools, automatic fiber quantification. Jason Eadman will later on elaborate that a little bit. And here they quantified, in this example, they quantified the optic tract and the optic radiation in healthy people and in people with retinal disease. And they looked where along the optic tract or along the optic radiation there was a change in the fractional anisotropy. And what we can see here is that the tract integrity is not affected in all parts of the tract, but in selected parts, like this one here. Then let's switch to whole brain analysis. The first one, and still in use, is voxel-based analysis or morphometry analysis. And this is basically an approach adopted by the analysis of structural MRI, like gray matter volume analysis, and basically the main steps here, besides of course the pre-processing, you do an registration of the T1 image to a template space. Usually this is done by nonlinear registration, warping. And in order to refine the analysis, you can identify major substructures of the T1, like gray matter, white matter, and cerebrospinal fluid, in order to improve this nonlinear registration. And then you warp, that means you nonlinear register the diffusion parameters to that template space, and then you perform the analysis. But in this approach, usually you apply a lot of spatial smoothing, which is necessary to get to solve the normalization problem, to get a good overlap of individual data with the template data, and also necessary for the procedures for multiple comparisons like the random field theory. It has a lot of benefits. It examines the whole brain, it's automatic, it's fast, and at least for T1 weighted analysis, it's quite well established. However, it has a few limitations, which are pointed out by Jones and some other colleagues. One limitation is the smoothing. This smoothing is smoothing across relatively heterogeneous white matter areas. And it may result in false positives and negatives. And the typical smoothing kernel, which is appropriate for T1 weighted analysis, that is about 8 to 12 millimeter, full width half maximum, may not be necessarily a good smoothing kernel for diffusion weighted imaging. And there is no clear procedure how to determine the perfect smoothing kernel. Nevertheless, it has been successfully applied, even in the early days by Christian Büchel. They published an article where they looked for differences in fractional anisotropy for handedness, and they found that the precentral gyrus contralateral to the dominant hand shows a stronger fractional anisotropy. So it is quite sensitive to aspects of brain microstructure. And more recently, a study by Sachi and colleagues, they looked at the mean diffusivity prior and following 2 hours of learning with a spatial learning task. And they found that there was a reduction in the mean diffusivity in the hippocampus and the parahippocampus area. Both approaches quite convincing. However, I mentioned that one criticism of this approach is that it heavily depends on the spatial smoothing criteria, which is here illustrated by the study of Jones in 2005. They compared the diffusion properties between schizophrenics and controls. In the diffusion parameter here was the fractional anisotropy. And they performed the analysis, the voxel-based analysis, with several smoothing kernels, with a small smoothing kernel, with 10 millimeter smoothing, with 12 millimeter, and with 14 millimeter smoothing. And the problem is that depending on the smoothing kernel, they found a reduction in fractional isotropy in schizophrenics, either in the right superior temporal gyrus or in the left cerebellum. So your conclusion strongly depends on the smoothing kernel that you choose. And that's something you should consider when you apply this analysis. As a consequence of that, the Oxford group has developed this track-based spatial statistics approach. It tries to solve these problems. The main steps here is that you do this warping or standardization on the fractional isotropy map. So you calculate the individual FA maps, then you nonlinearly register it to the standard FA map. You create a mean FA map in the standard space. You threshold that in order to get a skeleton, which is here indicated in green. And then you project the individual FA maps onto that skeleton. The way you do that is you take the maximum FA values in the individual brain in the neighborhood of the skeleton and project that to the skeleton. And then you perform a statistic, inferential statistic. They recommend a non-parametric statistic on the parts, on the voxels of the skeleton. So the benefits here is that it uses alignment invariant features. In a way, it's more robust than the voxel-based morphometry approach. And it also limits the number of comparisons that you need to make because you focus only on the voxels of the FA skeleton. I call it FA skeleton and rather than a tract skeleton, because as Alexander Lehmann this morning already pointed out, it's basically an FA skeleton. It's not really a tract skeleton. There are some little limitations with this approach, however, to be considered as well. One is this, there may still be some alignment errors with this approach. And this already mentioned that FA skeleton is not really corresponding to real fiber tracts. And also another limitation is that the analysis is limited to local maxima. Nevertheless, it has been has been used successfully. Here an example where they looked at changes in fractional isotropy using the TBSS approach in healthy people and in patients with Alzheimer's disease. And they found in the left anterior temporal lobe a reduction of fractional isotropy. Already mentioned that there was some criticism, including published by Bach, that this track-based this track skeleton is not really a track skeleton, but it's an FA skeleton, which may go through several different types of tracks, which is illustrated here. So the white one here would be the skeleton. But if you look at the color-coded primary direction in the back, it's going through different regions, showing different orientations of the tracks. That's likely corresponding to different tracks. There have been some improvements in recent years, which are, some of them are elaborated here. So for instance, you also implement the crossing fibers in the TBSS, or your skeleton is not based on fractional isotropy, but instead on directional information. But finally, I'd like to show you a little bit about surface-based analysis, which has not been used so much yet. But I think it is a good alternative to these other approaches. And I hope I can convince you that for some purposes it might be a valuable approach. A major thing here is that you take your T1 image and you reconstruct the brain. For instance, you can use the software tools from FreeServer or some other reconstruction process. You segment into white and gray matter, and then you create a white matter surface, which is illustrated here. And then usually you do a spherical registration, you inflate the brain to a sphere, and then you align this sulci and gyri of this spherical inflation to a standard brain. The advantage is that it preserves the major sulci and gyri structure of your individual brain. This is an example of how I apply this service-based analysis for fiber tracking. So you can seed the tracking algorithms by seed regions defined on the surveys. You identify them, then you track through the white matter. And then when you're done with the tracking, these tracks usually cross the white matter, gray matter boundary at some point, and you project the track probabilities at this white gray matter boundary back to the surveys. And then you can examine the endpoints of your tracking algorithms along the surveys using this spherical registration. So the advantages here are that you have a normalization based on major gyri and sulci, and you have a relatively close correspondence to cortical brain areas. A disadvantage here is that it limits your analysis to the cortical surveys, and it requires multiple analysis tools. There's no fixed one tool that is doing everything for you. Here are a few examples of that approach. In this example, I wanted to know the cortical connectivity of the auditory cortex. So we see that the tracking algorithm, it was probabilistic tracking with FSL, into the hashless gyrus, which is indicated here, and then tracked through the white matter to a set of 10 brains, and looked where along the cortical surveys these tracks terminated. And that's what we see here, the track termination maps. When we see it in auditory cortex, hashless gyrus, we have track terminations in the superior temporal sulcus, and the corpus callosum, as expected, the thalamus, not overly surprising. But we also saw track terminations in other brain regions, for instance, the medial occipital cortex, including the calcarean sulcus. You might think this is an artifact, that this might be a false positive. Well, one counter-argument is that it's quite robust across subjects. It's not just observed in one subject, but in many subjects. And the second counter-argument is that when we compare these track terminations with the brain areas that are engaged during a multisensory task, an auditory visual task, that means we performed an fMRI study and looked at the brain areas that are engaged in this multisensory task. And we see quite good correspondence between the track termination maps and the fMRI maps here. We also compared structural connectivity and functional connectivity using a service-based analysis. So here we looked at the connectivity of the cingulate sulcus visual area, which is an area responsible for ego motion, or to some degree relevant for performing ego motion. This was first described by Andy Smith, a colleague of mine. It has not been described yet in the monkey. It was primarily examined in the humans. And we wanted to know what's the connectivity of that brain area. So we performed structural connectivity, service-based, and functional connectivity, seed-based and service-based. And what you can see here is that there's quite some good correspondence between the structural connectivity results and the functional connectivity results. Finally, we also examined the connectivity profile, the cortical connectivity profile of two brain areas, PIVC and PIC, that are involved in visual vestibular integration. And I'm presenting that on Tuesday as a poster in case you're interested in. The main idea here was that it used to be that people thought PIVC and PIC are the same region. So we tried to identify, to separate these two regions in the brain. And one part of that was that we also looked at the connectivity patterns. And we compared the connectivity patterns of PIVC and PIC, and here we see the differences of the connectivity. Finally, I like to give you a few examples how to apply this service-based analysis for examining microstructure. Basically, instead of looking at the results of tracking, fiber tracking, you're looking at the results of certain diffusion parameters based on a diffusion model, fractional anisotropy, mean diffusion, and so forth. And you project these diffusion parameters of the white matter or the gray matter to the cortical surface. To be precise, we should call that superficial white matter rather than white matter, which I think gets clearer with the next slide. Here's an analysis pipeline, this time not myself, but by Wu, who also applied that, just to give you some variety of explanation. Basically, what we do is we project the diffusion properties in the neighborhood of the surface. In this graph here, you see the white matter surface here in yellow, the PL surface or PL gray matter boundary in blue. And we usually project the diffusion properties either from the gray matter on the surface or in the white matter below the white gray matter boundary. So precisely speaking, it's not that we examine the whole white matter, but instead just part of the white matter, which we call the superficial white matter. The major benefit here is, again, you benefit from the normalization based on major Chari and Solke, which is the spherical normalization. You have relatively good correspondence between cortical areas, and you can also get a good correspondence between functional MRI and diffusion weight MRI. The disadvantage is that you more or less ignore the deep white matter. But the superficial white matter is not a bad thing to look for. It is distinct in several aspects. With regard to the fiber architecture, it contains so-called local association fibers, which are sometimes also called U fibers, as opposed to long-range fibers. Also, the microstructure composition of the superficial white matter is different than from the rest of the white matter. For instance, it contains a high density of interstitial neurons, which are assumed to be associated with neurological and psychotropic disorders. Here an example how it was applied in order to look for developmental changes in young people aged 10 to 18, studied by Wu and colleagues. They did the service-based analysis and then did a group analysis on the surveys. And they found that there was a change in the fractional anisotropy and the mean diffusion along the surveys. I also did that, or we also did that with a different group of people. This time we have old people ranging from 20 to 80. We looked at the laminar profile of the diffusion properties, mean diffusion, fractional anisotropy across different levels of white matter and gray matter. We can confirm that there is fractional anisotropy is decreasing when you go from white matter to gray matter. And mean diffusion is also increasing from white to gray matter. Here in the bottom, we see across the whole surveys that there is a change in the diffusion properties with age. It's substantial, it's tremendous. Basically, across the whole surface, or the mean across the whole surface, the mean diffusion is substantially increasing. This is now a map of the changes due to aging. 4 different diffusion properties: mean diffusion, axial diffusion, and radial diffusion, and fractional anisotropy. We can see that this change is substantial. It's almost a little bit scary. But another thing that you might think is that, well, these changes look quite similar across different maps. So we performed a factor analysis in order to determine whether these changes in diffusion properties are just reflecting the same as we observe in the structural changes like cortical thickness and so forth. And we looked for independent components. This is the factor loading matrix for the different measures, cortical thickness, mean diffusion, axial diffusion, radial diffusion, fractional entropy, and so forth. We can see that these measures load at quite independent components, suggesting that the changes across different diffusion properties are not measuring the same aspect of aging that we see with cortical thickness analysis. We also looked at changes in these diffusion properties for macular degeneration, which is a retinal disease, and we wanted to know how that affects the calcarine sulcus. And we could observe a change in the mean diffusion in the most posterior part of the calcarine sulcus, the visual cortex, which represents the central visual field. Well, I'd like to finish now. I hope I could demonstrate that with diffusion analysis you see changes in brain plasticity, short-term and long-term, that the different diffusion properties, diffusion parameters are useful, that diffusion-weighted imaging is more sensitive than conventional MRI. But primarily I wanted to show you some overview of the several procedures for group comparisons that you could use. It depends on your exact study question which is the best choice for you, but be aware of the advantages and limitations of these approaches. And finally, I hope I could convince you that a service-based analysis could be a good alternative to your study. Thank you.